Hello everyone, welcome back to the new video of piezoelectric materials and smart materials. Today we will solve a very genuine problem related to the piezoelectric accelerometer in the course of piezoelectric materials. So let's read the problem. A piezoelectric accelerometer is being designed using PZT5S. So our material is one minute. So our material is PJT5H as a material. Of a piezoelect sorry, the moving mass of a piezoelectric material. The moving mass of a piezoelectric material is 5 gram, and the dimensions of piezoelectric sensor is 3 mm, 3 mm. There is the length and width, and 0.25 mm thickness. So in this piezoelectric accelerometer, we have to compute the low frequency sensitivity of the accelerometer in the picocoulomb per gram, compute the natural frequency of accelerometer, and we have to recompute all the relevant things like part A and part B for the 25 grams, right? So basically, this is the applications of the piezoelectric materials we use. We already discussed that the piezoelectric materials can be used as the sensor, and piezoelectric materials also can be used as a actuator, right? So we can use for sensor also, we can use piezoelectric materials for actuator also. We discuss about the different modes of piezoelectric materials, like we have 3 mode, we have 1 mode, and also we have 1 mode, yeah, or 3 mode, right? So basically the 3 mode is used for the uh, sensor and the transducer applications, like like this accelerometer, force and motion sensing. This is the application of force and motion sensing. And the 1 3 or 3 1 mode is used for the actuator applications, like bimorph. We like in the later video we discussed about the bimorph. If you forgot, please watch this video also, right? So let's go to solve this problem. So how can we solve? Low frequency sensitivity means like what is the applications of accelerometer, right? Accelerometer is measure the accelerations, right? And the piezoelectric materials, when we apply the force or the stress on the piezoelectric materials, it will generate the strain and it will generate the charge also, or electric displacement, the charge by area, right? So this is the converse effect of piezoelectric materials. So we have to compute the sensitivity means how much charge or how much electric displacement can be generated by the uh, this acceleration or the acceleration, right? Unit acceleration, right? Q by A. Try to understand that the sensitivity means how much charge can be generated by the unit acceleration, that is called the sensitivity, right? And the low frequency, so basically you know the what is the formula of frequency means under root k by m, as we know from our vibration course, that natural frequency is under root k by m. So we have to compute the k also for the piezoelectric materials. So let's see, and we have to compute again these things for 25 grams. So this is the table for PGT5H. So this is the typical formula of stiffness value. So what is the stiffness? Stiffness is resistance to deformation, right? Right. By the definition, stiffness is the force per unit deflection or force per unit elongation. that is the resistance to elongate a particular things. So Young's modulus is nothing but the sigma upon epsilon. uh, by solving we can get this value, right? And the reverse of this value is A upon SE TP. SE is basically piezoelectric compliance. uh, Compliance is the reciprocal or 1 by y, or it is the inverse of Young's modulus called the compliance, right? So this is the typical formula which we used in our calculation for the stiffness, because we have to compute the natural frequency is under root k by m, so we put the k value from here also, right? So it is very important to know that how can we write, or what is the formula of stiffness value, because mass is given, right? So this is the value of stiffness, typical stiffness. Also we have to see the uh, sensitivity formula. How can we interpret it, or how can we derive this formula? So we know that the electric displacement is d equal to dt plus epsilon e, where epsilon is permittivity of the material, piezoelectric material. E is the electric field. So basically we are not applying any electric field to the piezoelectric stack, or piezoelectric, sorry, piezoelectric material. We are not applying any electric field, so there will be only stress due to the acceleration, because suppose this is a piezoelectric material. So this has the length and width, also height, and this is moving by the a acceleration, right? So by Newton's law we know that the force is nothing but the ma, that is the inertia force due to the inertia, force due to the mass is ma. So this has the acceleration, that's why it's create the stress to the material, and this is represented here by the capital T. This is the piezoelectric uh, strain coefficient. So this is 0, because electric field is 0. We are not applying any external electric field. So by this simplifying we can get Q charge, because electric displacement is charge by area. Electric displacement is charge by area. This is P, because we are using the piezoelectric uh, area of piezoelectric material, right? Area means this length and multiply by width. So a and this T, stress is force by area, so area will cancel out each other, and Q equal to dF. F means force. By the Newton's law we can write the force, or the force due to inertia is ma. So let's put the value. So the ratio charge by area, sorry, charge by the acceleration is called the sensitivity of the piezoelectric material. Also I want to clear that this derivation is it's not accurate, because we are just trying to interpret it, or trying to matching the relations between q, a, m and d. So that's why this is the not actual derivation. If you want the actual derivation in the later videos, or like we are making many videos, so I will discuss the derivation of this program in those videos if you are interested in. So but this is true, like formula and the derivation is still true for the learning purpose, right? Sorry. So this is the our this is our sensitivity. So this equal to the m and d. So m is given, which is 5 gram and D is given. You can put the D three value here. 670 multiplied by 10 to the power minus 12 coulomb per Newton. You can put the D value from here and you can calculate the sensitivity. So let's see, this is actually minus, or this is minus, so minus minus get plus. So sensitivity, low frequency sensitivity is U double dot is acceleration. We are denoting U double dot by the acceleration at t time t. So this m we are writing in kgs, and this is uh, piezoelectric strain coefficient coulomb per Newton. So by multiplying this value will get in the pico coulomb per gram. So this is our answer for the low frequency sensitivity. So when you heard this term sensitivity, sensitivity means how much change in related or in those variables, right? Here the acceleration is very important, or the our output and input is basically, sorry, input is acceleration and output is charge. So output by input, that is the transfer function of this complete equation or the complete system. So we have sensitivity means transfer function actually. So this is sensitivity, how much charge is generated by the unit acceleration. So this comes out to be this value. And low frequency sensitivity, sorry, natural frequency means under root k by m. We know that the stiffness and mass and the square root of this is natural frequency. So this is like we already discussed that how can we derive the formula of stiffness. Stiffness is A S T P for the piezoelectric material. Here I discussed this derivation also, this. So by plugging all the values we can easily calculate the natural frequency or the short circuit frequency of the piezoelectric material. Short circuit frequency means uh, like this is a piezoelectric material, we are connecting this by the wires, so no electric displacement will be there, but the electric field will be there. So this is called the this is called the short circuit natural frequency or short circuit frequency. uh, this is the angular frequency, radian per second. If you want the frequency in the hertz or kilohertz, you can use this formula, omega equal to 2 pi f, and you can calculate the frequency, that is the original frequency, not the uh, radial frequency. So this frequency is this value, right? So this example will give us the uh, a feel of the application of piezoelectric materials and how we can like how can we use the piezoelectric materials in for the various applications, right? Thank you for watching this video.